Do I or
Looks like we're
there
muted.
we go.
Good.
Never mind. Um, all right. Hi, everyone. My name's Dr. Dave Clark, and I'm an associate professor in kinesiology and biomedical physiology and kinesiology here at Simon Fraser University. And I'm hosting today's um, seminar as part of the BPK seminar series, but also we've cross-listed it over with the SFU Sports Analytics virtual seminar series that I run. So we got a few more people than normal, which is great, and some new faces. So today we have Eli Mizelman, who's going to speak to us about evaluating physiologically interpretable models of athlete velocity duration data in NCAA men's soccer players and professional women's soccer players. So this is Eli's PhD exit seminar. It's a formal seminar given by those who are about to defend their dissertation. So Eli is defending next week on in the afternoon, which we're all looking forward to. Just a bit about Eli. He's a PhD candidate in here in BPK at SFU under my supervision. His research involves evaluating models of soccer player tracking data. Eli came to us with a MSc in kinesiology from the University of Saskatchewan and a BSc in medicine and life science from Tel Aviv University. He's currently an assistant professor of kinesiology at Briarcliff University in Iowa, and he performs nutritional and sports science consulting through his company EM Sports Science. He has presented his research in various forums, including the National Strength and Conditioning Association, Canadian Society for Exercise Physiology, and On the Podium Sport Innovation Summit. And with that, I welcome everybody, and we'll turn it over to Eli.
Thank you. So, good afternoon, everyone. Actually, good morning. It's afternoon here. Thank you for having me. It's a pleasure being here, and I've been waiting for this for a very, very long time. So today, as Dave said, I'm going to be talk about my PhD project that is about the evaluation of physiologically interpretable models of athletes' velocity duration data in NCAA men's soccer team and professional women's soccer players. So let me start with a brief introduction about aerobic fitness in soccer. As most of you may know, aerobic fitness is one of the most important aspects in soccer. And the best way to quantify aerobic performance is by using lab-based VO2 max test. However, the use of lab-based tests is very, very time-consuming and also requires different equipment. Thus, field-based tests to estimate VO2 max are much more popular among soccer teams, soccer coaches, and sports scientists. However, even the field-based tests, they require designated sessions for testing, and they cannot be done during a game or during a practice, meaning that they are still very time-consuming. Just a second. Okay. In addition to aerobic fitness, anaerobic fitness also plays a major role in soccer performance, as soccer is not an endurance sport per se. It is an intermittent sport. So, in fact, on average, a sprint or any other powerful activity, such as tackling or jumping, occurs approximately every 90 seconds, and it lasts between 2 and 4 seconds. Thus, it is of great interest of soccer coaches and for sports scientists to quantify both anaerobic fitness and aerobic fitness. However, once again, the use of laboratory-based assessments, such as the Wingate test, is time-consuming. So as you can see, we detected a need here. The need is to find a way to quantify both aerobic performance or aerobic fitness and anaerobic fitness in a manner that is less time-consuming or not time-consuming at all. So one possible way to do this is by using data from practice sessions or from games. And what do I mean by that? What kind of data is being collected through the game or through a practice in soccer? So in the last 10 to 15 years, player tracking using GPS-based devices has become one of the most common ways to monitor physical demands and training loads of soccer players. These devices, these GPS tracking devices, they usually measure external load metrics such as distance covered, velocity zones, acceleration metrics, and etc. But they, of course, like other GPS devices, measure also the velocity of the runs and the duration of the runs or the movement. In fact, not only that they measure that in high resolution. So they usually work in between 10 hertz and 20 hertz. So they sampling your location 10 to 20 times per second. Now, just to get an understanding why this is high resolution, your phone might work in a 1 hertz resolution. So it will sample one time in a second. So we wanted to see if we can use these GPS data that we have in order to examine the relationship between velocity and duration. Now, what do I mean by velocity and duration relationship? So for those of you who don't know, the relationship between the duration of a performance and the maximal velocity that can be sustained during that performance has been previously characterized by a model called the two-parameter critical velocity model. I will refer to this model as CV2 because it's a short for the two-parameter critical velocity model. Now, this model, as you can see in this equation, has 4 parameters. 2 of them are physiologically interpretable. I'll start with the 2 that are not. So the 2 not physiologically interpretable parameters are T, which stands for time or duration, and we measure that in seconds, and VT, which is the maximum mean velocity for that given duration T. Now, the other 2 parameters, they are physiologically interpretable. So as you can see here, what we have left is CV. CV stands for critical velocity. So every time I say CV, I mean critical velocity. And CV basically corresponds to the maximum velocity that can be sustained using aerobic energy, and thus it represents a parameter of aerobic fitness. The second one is D prime, okay, which is the distance that can be covered at velocities that are above critical velocity, so velocities that are faster than that. D prime is often thought as the work capacity above critical velocity, and it's mainly derived from anaerobic metabolism. Thus, both of these parameters, the D prime and the CV, are in interest of athletes and coaches because they correlate with lab-based physiological measurements of fitness. So here's an example to how this model that, as I said, describes the relationship between velocity and duration looks like using a graph. This is much easier way for me to understand that. So as you can see on this graph, first of all, on the x-axis, we have duration, that is in second, okay? And on the y-axis, we have velocity. It doesn't really matter what the values are, but you can see that the longer the duration, the lower the maximal mean velocity is, which kind of like makes sense. Now, if you're looking at this graph, you can see that critical velocity is basically the asymptote of the curve, and it's also equal to the second threshold. That's something that was shown before. Now, where's D prime on this graph? D prime is the area under the curve in the curvilinear part of this curve. So you can see if this is the curvilinear part, the area under the curve under any of these points is basically D prime. So all of these rectangles, all these 4 rectangles are basically equal to each other, and they all equal to D prime, okay? So D prime is the amount or the distance that we cover in velocities that are greater than critical velocity, okay? Now, over the years, the original critical velocity model, the CV2 that I just talked about, was developed to more advanced and updated version. One of these versions is the 3-parameter critical velocity model, or CV3. That one is probably the most appropriate one to use for GPS-based velocity duration data, because one of its parameters, or the additional parameter that we have here, is maximal velocity, or Vmax. That is something that can be straightforwardly estimated from GPS data. It's easy for us to basically take the highest velocity that we have, the maximal velocity of a player. So this parameter, maximal velocity, was missing in the previous model, as you can see on the plot that I showed before. You can see that here, basically, when we are reaching the shortest duration, The two-parameter model kind of like assumes that the max velocity is infinity. However, we know that this is not correct. All humans have actual maximal velocity. Um, but that's why it's an improved version um, of the previous model. Now, though the equation of this model, as you can see here, is a bit messier, it still contains the exact same parameters as before. So it still has Vt, d prime, Cv, which is critical velocity, E, and the new addition, Vmax, so maximal velocity, basically top speed or top velocity. Now, to confuse you even more, there was another model that was developed recently um, by Dave and other researchers that might be also appropriate for our purposes. That model is called the omni-domain velocity duration model, or OMVD as an abbreviation. So just like the previous one, just like CV3 that I showed before, the truncated version of this model, the OMVD, that works with durations that are 30 minutes or less, it features the same three physiologically interpretable parameters. Okay. So you can see in the equation that is even more complicated than the previous one, that we still have all the same parameters. So we have VT, we have D prime, we have CV, we have Vmax, and so on. Okay. Now, lastly, that's the last model that I'm going to talk about today, is a model that was developed and was called the five-parameter logistic equation model. I call it 5P or 5PL, just to save some time. This model is different than the other models that I mentioned so far. Why? Because this model is an empirical model. It was developed using a bunch of GPS data that was collected from soccer and rugby players. In other words, the developers of this model use the data that they have in order to come up with an equation that describes the relationship between velocity and duration the best. Thus, at least initially, the parameters did not have physiological interpretation. They purely found the best mathematical model that fit the relationship between velocity and duration the best. And you can see the equation right here. As you can see, there's more than those three. There's more than three parameters. In fact, there are five parameters. Now, with time or with the development of the model, it seems like two of these parameters, and you can see the list of them here, the five parameters. Two of them may represent physiological characteristics, and these are the C parameter, also called the lower asymptote, which may represent critical velocity, and D, the upper asymptote, which may represent maximal velocity. But as you can see, none of these parameters represent D prime. So here we have a model that has five parameters, only two of them are physiologically interpretable, and they are the equivalent of critical velocity and maximal velocity. So we don't have D prime whenever we work with the five parameter model. As again, this was the empirical model that was developed recently. Now, after I talked about all of these velocity duration models, comes the question. Has anyone ever researched velocity duration relationships using GPS data in soccer? The answer is yes, they did, but it was very limited. What do I mean by limited? These studies, three total, only use the CV2 model, so the simplest model that I mentioned at the beginning, or the empirical five-parameter model, the one without the D prime and the one with the biggest amount of parameters. No one has ever studied the CV3 model and the OMVD model. Okay. In addition, these three studies featured low resolution data in which only a few of many possible durations were sampled. And as I said, mentioned before, we wanted to do that in high resolution. I will explain exactly how many durations they use and how many we used in the next few slides. So all of this information led to a few open questions that we had going into this project. The first one was how do we actually model the relationship between velocity and duration using high resolution data obtained from GPS tracking system, and an emphasis on high resolution, which is something that was not done before. Two is, do different GPS tracking systems, and there are a lot of them, do they require different methodologies to model that relationship? Three, I just presented you 4 different models. We wanted to basically compare the goodness of fit of each model and to see, okay, which model is the best, which model is the worst, which one should we use? Is there one that is the best? 4 was what are the accuracy with which critical velocity and d prime estimates obtained from GPS data reflect their corresponding physiological values. So the CV that I obtain and estimate from GPS data, is it actually the actual CV that I can calculate in a CV test or in a field test or maybe in a different lab test to measure second threshold? Lastly, the last question is how we can use this concept in practice. How is this useful for practitioners? So the hypotheses that we had going into this project were, one, we hypothesized that the advanced CV models, the CV3 and the OMVD, will perform better for fit and velocity duration data of soccer players when we compare them to the empirical model, the 5P, and when we compare them to the simplest model, the CV2. Second hypothesis was that there will be a strong level of agreement between the model's parameter estimates, meaning CV and D prime, that we calculate from GPS data, and ones that are calculated either from a lab-based test or a field-based test. And 3, which is the practical part of the project, and I will talk about this part in more details in the last part of my presentation, is that high temperature will result in impaired soccer performance represented by lower values of critical velocity and D prime, but not maximal velocity. So we basically hypothesized that playing games in high temperature will negatively affect soccer performance. Okay, so let's start with the first study that we're done. Basically, what we did here is we examined and compared the goodness of fit of all the models that I've mentioned before. In other words, we wanted to know which model is the best one, if there is one that is actually the best. Now, as I said before, given that the CV3 and the OMVD models feature physiologically interpretable parameters, the CV, the D prime, the Vmax, we hypothesized that they would provide either equivalent or better goodness of fit than the 5-parameter model, the empirical one, and the CVT model, the simple one. So the participants and the data collection, we had 15 male players from the Seattle University NCAA Division I soccer team. We collected data, GPS data, for all players from all matches and training sessions during August and September of 2019. Overall, we had 42 sessions that were completed, and out of these 42 sessions, we had 7 that were actually official matches. Now, all the computations that we performed that using R with an R code that we developed. So as I said, we developed an R codes from scratch. That was a very hard task. That extracted and processed the data as follows. So first of all, we took the data, and let's pretend that we have 4 hours of data because that's when they turn on the devices. We wanted to first focus on the times in which we care about. So for example, we split the data into the first half and second half if that was a soccer match. Then we moved any NA values if we had any, and we exclude data that had low quality GPS signal or data that gave us unrealistically high velocities. So velocities that are above like 43 kilometers per hour. So that's kind of like was our way to clean the data and focus on the data that matters and also to use high quality data. Then we applied functions that calculated the moving average for the velocity data for duration from 0.1 seconds to 600 seconds in 0.1 seconds increments. That means that we had total of 6,000 durations from 0.1 to 600 seconds moving in a 0.1 increment. So that is a lot. Next, the highest mean velocity for each of these 6,000 durations was extracted. And we repeated this process for all data sets for each player, obtaining the athlete's velocity duration profile by documenting the highest average velocity for each duration across all files. This analysis resulted in what we called the global velocity duration profile, and we had that for each athlete. Lastly, what we did is we fit the 4 mathematical models that I mentioned before. So here's an example for one global velocity duration profile from one player. So you're able to see how every duration from 0.1 seconds to 600 seconds, for every duration, we actually found the highest mean velocity from practice and game data and then plotted it. So basically, we broke down all the sessions into segments of 0.1 second, 0.2 seconds, 1 seconds, up to 600 seconds. And we found the best one, the one with the highest mean velocity. And then we plotted that. Now notice that we're getting a very similar plot to the previous plot that I showed to you before. Again, this curve contains 6,000 points. Okay, that's what I want to emphasize that it was high resolution. But we did that for all players. This is just an example for one player. Now, to test our hypotheses, we operationally defined model goodness of fit as 3 things. First one is root mean square error, or RMSE. This is the standard deviation of the model residuals. And for those of you who don't know, model residuals are the difference between the predicted and the observed value of a variable in the model. The second definition that we had was, or the second way that we basically used in order to define goodness of fit or quantify goodness of fit was using AIC. AIC is calculated by obtaining the maximum value of the likelihood functions for the model and the penalty term due to the number of estimated parameters in the model. So just to clarify, likelihood measures how well a model explains observed data by calculating the probability of seeing that data under different parameter values of the model. Regarding the penalty, the more parameters we have in the models, the higher is the penalty that we will get. Lastly, number 3 was using BIC. BIC is very, very similar to AIC, only that the penalty term here in using BIC also depends on the sample size. Okay. Overall, models with the lowest values for all the 3, for RMSE, AIC, and BIC, interpreted to exhibit the best goodness of fit. So basically, we're looking to get the lowest values possible. That means that the better fit, the goodness of fit is actually better. Now, in addition to that, to statistically test the research hypothesis, we applied the linear mixed effect models to assess the model goodness of fit in a way where AIC was the response variable, and the model types and player ID were the explanatory variables. So the model types was designated as a fixed effect, and player ID was designated as a random effect. Lastly, to compare the CV and Vmax estimates between the models, we used mixed effect models featuring the CV or Vmax as the response variable, and model types and player ID as the explanatory variables. So here's an example for the result that we've seen using a graph form. Okay, so this is basically a representative velocity duration profiles of one player and the fit of all the 4 models. So each square is basically a model here. You can see that, again, we have the duration on the x-axis, the maximum mean velocity on the y-axis, and you can see that we have the colorful solid lines. Those are the model fit, and the gray points behind them, I hope you can see them, those are the actual data points, okay? So we got this kind of results for each player, 4 times, because we use 4 models. Now, after fitting the different models for each player, here I'm going to show you the results in a form of a table. Now, again, instead of showing you 15 tables like this, because we had 15 players, I decided to summarize all of them into one table. So here you can see a kind of like a summary of everything that we got for all 50. So what you can see here is that one, differences between the players' velocity duration profiles and the corresponding models were evident. And two is that the CV2 model exhibited the highest goodness of fit of values by far. So that means that these values, they are the highest, and they're even positive while the rest are negative. So that means that the goodness of fit of CV2 is the worst. Okay, remember, we need lower values when it comes to goodness of fit. So these observations were supported by the statistically significant likelihood ratio test for the player ID random effect from the mixed effect models for CV and D prime. In addition, the differences in values between CV2 and all the other models were statistically significant. Okay, so CV2 was statistically significant or statistically significant than the other 3 models that I talked about. Now, while the differences between the other 3 models were not statistically significant, we still had some sort of an order. So the highest goodness of fit, the highest goodness of fit was the 5PL model, followed by the CV3 model, followed by the OMVD model. So, just a second, as you can see in this table, once again. So the 5-parameter model will have or had the lowest values, meaning it has the better, or the highest goodness of fit, followed by CVT 3, and followed by OMVD. So, what is so special about this study? As I said before, this was the first time or what we did was we generated high resolution, and emphasis on the high resolution velocity duration profiles derived from GPS data collected from NCAA soccer athletes, followed by testing the ability of the CV models to fit the data. In other words, our study contributes a new methodology that can be incorporated into the toolbox of sports scientists and coaches for future use. So this methodology of ours, meaning the R code that we developed, it generates high resolution velocity duration profile from raw GPS data really, really fast. As an example, just so you understand how fast it is, the code is able to generate the maximal mean velocity profile for a player from a data set of approximately 38 sessions, either a game or practices, in less than 1 minute. In addition, as I mentioned before, our velocity duration profile were generated feature far higher resolutions than previous studies. So previous studies, I don't remember if I mentioned that before, they either used 6 durations or 21 durations. We used 6,000 duration. Now, how can we apply this in practice? So first, everyone can now use our code to compute and model high resolution velocity duration profiles from GPS data. And they can use it to quantify peak run-in demands, for example. Second, the R package that we developed can be imported by users, and its functions can be integrated into different data analysis workflows. So the code is actually open source, and it's fully modifiable by users. Lastly, we learned that the CV3, the OMVD, and the 5PL models, all of them can summarize the profiles and can be used to longitudinally monitor individual players. or maybe to compare positional demands and other ideas. So after we compare the different models and we try to find which one is the best, or maybe which one is the worst, or which one we should use, our next question was to examine the agreement between the CV model estimates and lab-based and field-based tests. Okay. So as I said at the beginning, there is a growing need for unobtrusive ways to assess player athletic abilities that do not require dedicated time for testing. Now, if you think about it, the CV model estimated from player tracking data could be a potential way to do so. It's a potential way to assess player aerobic and anaerobic fitness in an unobtrusive way. So that's what we were trying to examine in this second study of ours. So to make sure that these models can actually be used to monitor fitness, their parameters must correspond to measure physiological values. Now, in the past, in not using soccer data, previous studies actually evaluated the associations of CV with velocities at second threshold that were measured using physiological variables and found that one, CV is well correlated and almost equal to velocity at MLSS, or the second threshold. And two, CV showed significant positive correlation with VO2 max at anaerobic threshold, such that it could be adopted as an index of endurance performance. So we know these, we have these findings from previous research that was done, I believe, on runners. Now in soccer and other team sports, we have a bit of a challenge when we are trying to do the same. Why? Because soccer and other team sports are in nature, as I said, they're intermittent, meaning that it's really hard to find, for example, a true maximal all-out bout of running that lasted 400 seconds or 500 seconds or 600 seconds. It's just not something that happens naturally in soccer. So what I mean is that these non-maximal efforts that we have from GPS data, they may result in inaccurate estimate of CV model parameters. However, that doesn't mean that it's useless. The CV models may still contain useful information about athletes' fitness if strong associations exist between the parameters and their corresponding physiological measures. So for example, fitter athletes should produce velocity duration profiles that are shifted upwards compared to those of athletes who are less fit. Another example can be the development of fitness in a single athlete that may manifest as increased CV from velocity duration profiles collected over time. So the purpose of this study, the second study, was to examine the agreement and association between critical velocity measured from GPS data with lab and field-based measures of the second physiological threshold. The lab-based measures of the second threshold was the velocity at respiratory compensation point, so our CP, determined from a graded exercise test using a treadmill and a metabolic cart. The field-based measures of the second threshold that we used was the CV estimate from the CVT model fit two runs that we had. So we had the athlete run two distances, 800 meters and 1600 meters. And from the results of these, we basically fit the CVT model and got their critical velocity estimates. Our hypothesis was that CV estimates from the velocity duration values will be biased downward compared to the measures of second threshold. But the bias would be consistent across players, and the values would be associated. It will be biased downward because of what I just explained about the the fact that the soccer game is intermittent in nature. So the participant data collection for this study, it was very similar to study one. It was actually the same exact participants. The only addition that we had in this study is we had the gas exchange data for the lab-based test. Okay, so we used a metabolic cart and a treadmill, and an incremental test to exhaustion that was conducted on each of the players. In this case, we had 14 players who did this test. Now the measures, the measured variables included VO2 max, gas exchange threshold, and respiratory compensation point, RCP. The lab-based measures of second threshold in the study were the VO2 and the velocity at RCP, respiratory compensation point. Addition number 2 that we had, excuse me, in the study was running data, so time and distances, and that was basically our field-based test. So the field-based second physiological threshold was calculated using the CVT model, meaning we use linear regression to estimate the CV and the D prime parameters value from 2 set distances run, 800 meters and 1600 meters. Those was performed by 13 athletes on 2 different days. When it comes to testing of our hypothesis, we used Blend-Altman method to assess the bias and the limits of agreement between CV estimate and the measures of second threshold. So this is how it looks like. For those of you who never have seen Blend-Altman plots, I'm going to explain this. In each of these figures, you can basically see the average of the model estimates and the result from the lab tests on the x-axis. Okay, so you can see that this is the average. This is the average that we get from the lab test and from our model. On the y-axis, we can see the difference between the two. So if that was the average between the two, now we can see the differences between the two. So what happens here is that we get the velocity at respiratory compensation point minus the model estimate. Okay. Now each of these figures basically represent a different model. You can see that we have 4 because we have 4 different models. Now the solid line in the middle, all of these, the solid line represent the average bias, okay? And the dashed lines at top of the bottom, they represent the limits of agreement, meaning that this is plus and minus of 1.96 standard deviations, okay? So the limit of agreement would basically be this minus this value. Now, let's look, for example, at the CV3 model. We can see that we had an average bias of 1.36 meters per second, meaning that our model, on average, underestimate in 1.36 meters per second when compared to the lab-based results that we had. Okay, now that is quite a lot. Now, if we keep looking at CV3 as an example, we can see that the limits of agreement were 1.06 meters per second. So I get to this by subtracting 0.33 from 2.39. Now, so this was 1.06. If I'll go to the 5 parameter and I will subtract 0.2 from 2.82, I get limits of agreements that are 2.8. That is double, okay? So now that you are understanding what we are looking at, and before I give you a second to look at all the models, I would like to add that in all of these models, you can see that 13 out of the 14 data points, that is 93% of the points, lay within the plus minus of 1.96 standard deviation. Usually it's considered in blended plots that 95% of the data, if it lays between the limits of agreement, that is considered to be a good level of agreement. So I'll let you look at for a second while I take some water. And we'll move on to the next comparison. So while in the previous slide, I compared the agreement between CV estimates from our models and lab-based tests, here you can see very similar results, only that here we compare our model estimates with the field-based tests. So the critical velocity that we estimated from these two runs that I mentioned before, okay? So now that you are a pro in reading blended plots, you can see that the average biases were, for example, 1.9 for the CV2 model, 2.6 for the 5PL model, 2.4 for the CV3 model and the OMBD model. And you can also see that the limit of agreements were 0.9 for the CV model, 1.4 for the 5PL model, and 1.1 for CV3 and OMBD. Lastly, here again, we have 13 points in total, not 14, because we had one less player that did this test. We can see that 12 out of the 13 data points lay within the limits of agreement. So that is 92% of the data points they lay within the limits of agreement. Remember, 95 is considered to be good levels of agreement. So what does all of this mean? If I were to sum this up, CV estimates from all four models were lower than velocity at respiratory compensation point, meaning that all of our models underestimated the second threshold. Okay. Now, although, as I said before, 92 to 100% of the points for each CV model lay inside of the limits of agreement, which supposedly looks good. The limits of agreement, as I mentioned when I compared the 5PL to the CV3, they were very wide. So it's indicating that the estimating of one variable from another may result in a significant error. So I'll just give you an example to explain this. If the velocity at respiratory compensation point were to be estimated using the CV value from the CV3 model, according to the limits of agreement that we have, it indicates that the result could be up to 2.3 meters per second below the actual values. So the underestimation can be gigantic. This well exceed the acceptable values, and that acceptable value is 0.2 meters per second. So what I'm trying to say is that the underestimation is way too high, and thus this is not really acceptable to use in practice. Now, in addition, it's also important to note the limitations that we had in this study because we had quite a few. So the first limitation was that the lab and field testing were not conducted at the same time as the GPS data collection. That was just out of our control. Also, it was relatively short data collection period, only 6 weeks. And lastly, the field CV test lacked quality. So we were only able to collect running data for 2 distances. That is why we had to use the CV2 model, which we know is less accurate. All the other models require at least 3 distances, but unfortunately we couldn't control this and we only got 2 distances. Also, the more running distances you have to calculate CV, the more accurate the estimate is. So we practically used the minimum, and that's why it's not so accurate, but that was beyond of our control. So according to our findings, parameters from the CV models of velocity duration profiles cannot be used to infer aerobic fitness. However, this was the first study to compare CV estimates from velocity duration profiles generated from GPS data to test of the second threshold. So it may serve as a first step in the development of a new unobtrusive ways to determine aerobic fitness throughout the season without dedicating testing. In order for this to happen, future research should include longer data collection, CV tests with at least 3 distances, and training sessions that may include all-out efforts in different durations to minimize the underestimation of the CV model due to the nature of the soccer game. Now we're getting to the last part of my presentation. And that's going to be about a way to apply our methodology in practice. So we try to examine the association between CV model parameters and ambient temperature. So this time we use data from elite female soccer players from the Canada Soccer Women's National Team. So a bit of a background before I dive into this research. We all know that high ambient temperature impairs performance in general, and that is also the case in soccer. So previous research found that high ambient temperature, more than 30 degrees Celsius, were found to impair lengthy exercises when compared with lower temperature. And that when comparing soccer games in higher temperatures to normal or neutral temperatures, multiple studies found that higher temperatures negatively affect both the total distance and the high velocity rate. Now, because of the detrimental effect of hot temperatures on performance, athletes use chronic heat alleviation strategies prior to competing in these environments. These strategies basically results in physiological adaptations that improve their ability to tolerate high temperatures. Now, its critical velocity corresponds to the maximal oxygen uptake and to the second threshold. In theory, we would be able to use GPS tracking to track the improvement of both variables without the need for any other equipment or tests. And we can do that multiple times throughout the heat elevation strategy. Moreover, we would be able to detect the athletes that are more susceptible to higher temperature and maybe optimize their alleviation strategies. So this kind of application will be of great values in competitions that take place in really, really hot environment. So the purpose of this study was to assess changes in soccer players' performance under different combinations of ambient temperature as measured by CV, D prime, and Vmax values. We hypothesized that CV and D prime will be inversely associated with temperature, while maximum velocity will not vary. So the participants and the data collection here, they were different. We had 6 female players from the Canada Soccer Women's National Team. The data was collected by the team, and we had data from 6 players for 6 months in 2018, and that included matches, friendly matches, and practices. In this study, the GPS-based velocity duration data was collected by a different GPS system, which means that it required a completely different code. So we had to develop a different code in order to work with that system. So in a very, very similar manner to what we did before, we split the data into sessions, we cleaned the data, we took out low quality GPS signal, unrealistically high velocities. Also, we had to do some conversion with the times in this system. And then basically we repeated the very, very similar process that I mentioned before using the Seattle soccer team data. Now, the only thing that was different here is that upon completion of the data extraction and processing, we automatically added ambient temperature values that were collected from the closest meteorological station to that game or to that practice location, and also the right time in which that happens, okay? And then we used the CV3 model to fit the velocity duration profiles using nonlinear regression, and the association between model parameter values and temperature were analyzed using linear regression. So before we get to the results, and because I don't have much time, I just want to mention that because this was a different data set and we used different players, we also repeated the same step that we did in the Seattle University. So we fitted all models and compared the goodness of fit. I'm not going to get into that in details because I don't have a lot of time, but I can tell you that in this case, it was funny because actually the CV2 and 5PL were actually the ones with a better goodness of fit. However, for our research question, we needed a model that had all the three parameters. So we needed a model that had D prime, CV, and Vmax. And as you remember, only CV3 and OMVD had these. So we basically had to choose the best out of these two models. So we went with the CV3 model because it has lower values of AIC, BIC, RMC. So this is how our result looked like. In this case, we're looking at the association between CV, so that is the y-axis, and temperature, the x-axis. Each data point represents a game or a session. Out of the 6 players that you see here, 1 player had a statistically significant high inverse correlation between CV and temperature. And another one had a moderate inverse correlation that was not statistically significant. The other players had no correlation whatsoever. If I'll show this in a form of a table, here you can see that I have statistically significant correlation, and the R square was 0.55. Well, this is the other play that I showed you before, and the p-value was 0.2, so it was not statistically significant. Now, moving on to the comparison with D prime. So again, in this case, we have D prime on the y-axis, temperature on the x-axis, and each data point represents a game or a session. Out of the 6 players that you see here, 1 player had very high statistically significant inverse correlation between D prime and temperature. So that would be this player. And other 2 players had high statistically significant inverse correlation, these 2. So you see that the R square value here is 0.89, and here is also it's a bit lower, but still high, 0.63 and 0.5. So if I show this in the result, here you can see the results again. Those are the 3 players that we had, and we can see that there are significantly statistically significant differences or associations for these 3 players. Lastly, when it comes to Vmax or maximum velocity and its association with temperature, here's what we saw. Again, Vmax is now on the y-axis, temperature is still on the x-axis, and each data point represents a game or a session. Out of the 6 players, only 1 player had high statistically significant correlation between Vmax and temperature. Again, in a table format. So all in all, if I kind of like conclude all of these findings, for CV, we found only 1 significant inverse correlation with temperature. This may imply that this player aerobic fitness may be negatively affected by higher temperatures. Now, the regression lines for the other 4 players was quite negative, although the correlation did not reach statistical significance. These results basically partially support the hypothesis that high ambient temperature have negative effects on critical velocity value. Similar results were observed in the D prime analysis, in which 1 player exhibited a very high statistically significant inverse correlation between D prime and temperature. And as I mentioned before, the other 2 had high inverse correlation that was statistically significant. So these results basically imply that the player's D prime decreases as ambient temperature increased, and that the player's anaerobic fitness may be negatively affected by higher temperatures. When it comes to Vmax, other than 1 player, there was no statistically significant association between Vmax and temperature, which also aligns with our hypothesis that ambient temperature should not affect maximal sprinting velocity. Now, it is important to note some major limitation in this study as well. One is that due to the circumstances that were beyond our control, the number of sessions of data we had for each player was much smaller than expected. We expected many more sessions, and we only got a few. Approximately, we had 7 sessions per player. Thus, as expected, in a post hoc power analysis we did, we found a low statistical power because we didn't have enough sessions. In fact, out of all the analysis that we run, you don't need to go over this tables. I just circled the one that had power that is higher than 0.8. So most of our analyses did not have the proper power. Another limitations other than the power is that the highest temperature that we measured in the study were less than 28 degrees, which is usually the points where hot environments start to have an effect on performance. So maybe the temperature were not high enough in order for us to see a correlation, if there is indeed a correlation. So to sum up, our methodology and results motivate additional study in which CV models parameters from velocity duration profile are used to examine temperature effect in relative ease. In addition, we decided to perform power analysis to determine power in the study. And by doing that, in a way of kind of like making lemonade out of lemons, we try to help future researchers to find the number of data points or sample size that they would need in order to evaluate this association um, at a meaningful level of precision. Now, due to a lack of time, unfortunately, I can't go over this, but I just wanted to say that even though we had really low power, we tried to prevent future um, studies from basically repeating the same thing. And we kind of like gave a way for them to answer these two questions. How many games would be needed to determine whether a relationship between temperature and these parameters exists for a single player? And how many players who play X amount of games would it take to determine whether a relationship exists on average? So I'm not going to go over this example just because I ran out of time. Um, and the last thing, this would probably be my last slide, um, that I want to talk about is about future research in this field. So I believe that future research in this field should focus on the optimization of these models that I presented, and or on the development of maybe better models. Um, this should be done using bigger data sets with more participants, with more sessions across different GPS tracking system. Because as I showed you, there is a difference between one system and another. Once the optimization of the best model or models is achieved and validated, scientists will be able to implement this model in practical setting, such as using velocity duration profile to quantify intensity training load, maybe examine the effect of environment on performance, or maybe monitor fitness throughout the season. So I would like to thank you all, and I would like to thank all the people that you see on this list, and that list is alphabetical and nothing more than that. And also for all the funding that I get throughout my years. So I'm really thankful for all of these organizations and these people. And I hope I didn't take too much of your time, and I will answer any questions you have.
All right, great job. Thanks, Eli, for that talk. So we'll do about 10 minutes worth of questions if that's okay with everyone. Again, feel free to leave if you have other commitments at 12:30. Eli, are you okay to stick around for about 10 minutes?
Yes.
Perfect. Okay. So we'll open up the floor to questions. If you do want to just maybe raise your hand and I'll call on you to ask your question. So maybe while we're waiting, so how many participants and games would we need given the variabilities that were observed and the sort of effect sizes that we're expecting?
So here I didn't go over this slide just due to lack of time, but basically using the effect size values, we calculate the average effect size for a single player in our research. That was a 0.33. In order to detect a similar effect size with alpha level of 0.05 and power of 0.8, the total sample size, meaning the number of sessions that are needed per player, would be 26 sessions. We didn't have 26 sessions. Also, the combined effect size for all players that we had in our research was 0.06. To detect a similar effect size with the same alpha level and the same power, the total sample size that we need would be 133 sessions. So you could see that we were very far from that, but at least, I mean, low power results or studies should be still published because of that. And we kind of like we didn't plan for our power to be so low or for our sample size to be so low, but this is kind of like a very natural thing when you work with professional teams. You plan one thing and then it just doesn't work, maybe, and you can't control that unless you are part of the team or unless you are the coach. So our goal as scientists is basically to get as much as you can, even if you didn't get enough. Um, so I was really disappointed that I didn't have a lot of sessions. I was really disappointed that I didn't have higher temperatures. But with what I had, I kind of like tried to maximize and kind of like try to help future researchers to gain some knowledge or some beneficial information from what we did.
Just to follow up on that, you what would it be like a way, like a statistical inference type to use when you have underpowering? Like, what would might be an alternative approach that one could use in this type in this context, especially like you said, dealing with professional athletes, you're often underpowered and have very little control over the collection of data and such.
So you mean other than increasing or having enough like a big enough sample size?
Yeah, so like there's the when you talk about statistical significance, that's sort of the frequentist approach to statistical inference, and there's another type of major type of statistical inference where which is particularly useful when you have underpowered situations. Does that ring a bell?
I assume you're referring to Bayesian statistic.
That's right. Yeah.
Uh, but yeah.
Yeah, so just, you can imagine that, with this sort of scenario that maybe trying to develop priors and then just updating those
Uh-huh.
distributions based on the data that you do have to try to more individualize it to or to customize it to the players that we're monitoring. That would be maybe an alternative approach
Hmm.
altogether here.
Okay. Thank you.
Hey, is there any other questions?
I could ask one.
Sure. Hi, Jody.
Hi, Dave. Hi, Eli. It was really nice to see the final product of your presentation. I've been
Thank you.
watching your poster presentations and things for a while, so it's nice to see that you got it all finished. Congratulations.
Thank you.
Um, I'm wondering, given that, so I work at On the Podium, and so I'm thinking of your work as how it would be applied in the sports setting. And the real value that I see here is that it would probably be used to assess and monitor an individual athlete and how their own profile changes over time. So,
Mhm.
if that were what we were trying to do, how far do you think this project brings us along that road? And where do you think the next step is in being like, what's the sort of the thing that would keep us from being able to implement that uh, more effectively right now?
So I think that what makes this idea or methodology special is that it's very individualized. So we can work with uh, each player and compare players to themselves and monitor their fitness throughout the season, or maybe find out which are the players that are more susceptible to it can be high temperature or it can be elevation. So it gives a very different your unique way to work with a team or with athletes as individuals because they're very different. Now, the thing that we're missing the most here is we need to repeat, or we need to have more studies that will basically optimize everything here. I mean, I presented what we did, and obviously it looks like we had a lot of limitations, and it's not ready for prime time. But there's something in here. There's something in here that if we will all work together and we'll keep using bigger data sets, and we keep using or working on developing newer models or optimizing models, I believe that at one point we will be able to come with a model that will be very useful and very accurate or very reliable. And then that could be used for many, in many ways, whether it is if you are monitoring the game demands, or whether it is you monitoring the fitness on a weekly basis without even having any tests, or not even on a weekly basis, maybe even on a bi-weekly basis, or because we have the data already. We collect the data all the time. The data is there. The thing is that nobody's using the velocity duration data nowadays. So I think that most of what people use GPS for, it's kind of like, it's not individualized, meaning that one of the most common metrics is player load. Now, player load is basically a summation of all accelerations and deceleration in a session. But we don't really know what it means physiologically. We don't know. It's basically a number, um, and it doesn't tell us much of how this correlates with aerobic fitness, anaerobic fitness. Um, Here we have some sort of data that we can basically use that in order to replace um, testing throughout the season. And not only that, that maybe instead of having 2 times during the season we have testing, we're able to basically test every single time. Now, maybe that is also important in cases like, let's pretend that we have a player that had an injury and didn't play for 2 months. And we want to see how his aerobic fitness is progressing. So we don't have to designate one person that will work with him, that will take him to a lab, that will measure his VO2 max a week after week after week. Here we just let them participate and basically get that information while they participate. So I like the fact that it's really individualized, and can be used for many different uses, and that it's just very easy to get all of this. Because to tell you the truth, at the beginning, before we developed the code, it was very hard. But now somebody can just get the velocity duration profile in, just by importing the data and clicking a button, and it's there. Now it's a prototype. It's not ready. I understand that, but I think that there is a potential here. And that can also work for other sports, not just soccer. For example, I see that this may work for hockey or rugby, and this can be used in order to see if, for example, we have the most freshest players on the ice or on the field, by calculating, for example, the amount of D prime that they have at any given time. Um, I I can think of a lot of uses for this. That the main thing that we have to work on is optimizing, using more data, using uh, more sessions, um, maybe using data from different um, teams or different levels of soccer. But I can also believe that that could be used in different sports as well. Dave, you were muted.
Sorry, I think I was muted there. Thanks, Jody, for the question, and Eli for the response. Okay, so we're up against 12:40 here. I think we're gonna end the recording and the talk here. So I want to thank Eli again for the presentation, and thank everyone for joining. And take care.
Thank you.
Eli and Dave, could you guys hang on for just a minute?
Yes.